What if the universe is not something you look at, but something that looks back, not as metaphor, not as philosophy, as a result that comes out of the most tested, most confirmed, most precise body of science in human history? The kind of result that gets printed in textbooks with careful language and extensive qualifications and then quietly dropped from the conversation before anyone asks the next question. Here is the thing that nobody leads with. We have spent 100 years building the most accurate physical theory ever produced. Quantum mechanics predicts experimental outcomes to more decimal places than any other framework in science. It works. Every test, every application, every technology built on its predictions confirms it. And sitting at the center of that theory, unresolved, formally documented, never explained away, is a result that says the act of observation changes what is being observed. Not because of instrument noise, not because of physical disturbance, because something about being watched changes what a thing is. That is not a loose interpretation. That is what the data shows. And the field has spent a century finding careful ways to discuss it without following it to where it leads. Look at what we actually know. Across quantum physics, cosmology, geology, and philosophy, independent lines of research keep arriving at the same boundary. Reality, at its most fundamental level, does not appear to be indifferent to being observed. The universe does not sit still while you examine it. It responds. And the response is not random, and it is not noise. It is systematic, it is measurable, and it is reproducible in any laboratory on Earth. What you cannot do is explain it. Not fully, not in a way that closes the problem. The explanation has been missing for 100 years, and the gap is still there, noted in footnotes, discussed in conferences, never resolved. Here is the central tension. We assume by default that we are the ones doing the watching. We point instruments at the sky, we build detectors, we design experiments. We are the observers, and the universe is the thing being observed. That assumption feels obvious. It is also, at minimum, incomplete. What the data from multiple independent fields keeps suggesting is that the relationship runs in both directions. That observation is not a one-way street, that the universe is not a passive backdrop against which human history plays out, and that if the relationship is mutual, if the watching goes both ways, the consequences of that are something we are only beginning to trace. Before you can understand what that means, you need one entry point, just one. The rest follows from it. In the early 20th century, physicists discovered that particles behave differently depending on whether they are being observed. Not marginally differently, categorically differently. A particle passing through two slits with no detector present produces an interference pattern on the screen behind it. The pattern only makes sense if the particle passed through both slits simultaneously, as a wave, as a smear of probability spread across space. The moment you place a detector at one of the slits to find out which one the particle actually went through, the interference pattern disappears. The particle stops behaving like a wave and starts behaving like a definite object that went through one slit and not the other. This is not a quirk of early equipment. It is not a measurement artifact. It has been tested with electrons, atoms, molecules, photons. It has been replicated across a century of increasingly precise experiments. The result is the same. The particle knows it is being watched, and it behaves accordingly. That is the piece that does not get followed far enough in most public accounts of this. The result is usually presented as interesting, as strange, as one of those counterintuitive features of quantum mechanics that you just have to accept. What it is not usually presented as is what it actually is. A formal, documented, unreplaced result that implies the universe is not a collection of objects with fixed properties waiting to be discovered. It is a system in which what is real, what is definite, what actually exists in a concrete state, depends on the act of observation in a way that has never been fully accounted for. We understand the result. That is not the problem. The problem is what the result means. And that is the part that nobody in the field has found a comfortable way to say directly. In the early 1800s, Thomas Young sent light through two narrow slits and changed everything, though it took another century before anyone understood exactly what he had changed. The setup is simple. You fire particles at a barrier. The barrier has two narrow openings. On the far side of the barrier is a screen that records where the particles land. That is the entire experiment. What you get back should be straightforward. Two slits, two bands of impact marks on the screen directly behind each opening. That is what common sense predicts. That is not what happens. What you get instead is a striped pattern. Alternating bands of high impact density and near zero impact density spread across the screen in a pattern that only makes sense if the particles are behaving like waves. Waves from the two slits spread outward and overlap. Where the peaks meet, they amplify. Where a peak meets a trough, they cancel. The result is a pattern of bright and dark bands, an interference pattern, the same thing you see when two sets of ripples cross each other on water. That is a wave behavior. The particles are not behaving like particles. They are behaving like waves. Here is what that means physically. For an interference pattern to form, the wave has to pass through both slits at the same time, not one slit or the other, both, simultaneously. Which means each individual particle, each single photon or electron fired at the barrier is somehow going through both openings at once, not splitting, not taking one path or the other, existing in a superposition of both paths until it hits the screen and registers as a single point of impact. The wave passes through both slits. The particle lands in one spot. Both things are true of the same object at the same time. That is what the data shows. Now here is where the experiment stops being physics and starts being something the field has not found a clean category for. You want to know which slit the particle actually went through. Reasonable question. You place a detector at one of the slits. The detector barely interacts with the particle. In some versions of this experiment, it exchanges so little energy with the passing particle that any physical disturbance is negligible. The particle goes through the apparatus, hits the screen. You check the detector's record to see which path it took. The interference pattern is gone, not diminished. Gone. The screen now shows two bands of impact marks, exactly what classical physics predicted before any of this began. The particles are behaving like particles again. They are going through one slit or the other. The wave behavior vanished the moment you introduce something capable of recording the path. Why is that not the headline every single time this experiment is mentioned? Because what it says is that the physical behavior of the particle changed based on whether information about its path was being recorded, not based on a physical collision, not based on energy exchange, based on observability. The particle does something different when its path is knowable than when its path is not. The field has a name for this: wave function collapse. The quantum superposition of both paths collapses into a single definite path once a measurement is made. The mathematics handles it cleanly. The mechanics of why it happens are not resolved. That is not a minor gap. That is the central unsolved problem in the foundations of the most accurate scientific theory ever developed. Then, Wheeler made it worse. John Archibald Wheeler designed a variation of this experiment that has a specific technical name, the delayed choice experiment, and a specific result that has no comfortable interpretation. The setup is modified so that the decision to observe or not observe which path the particle took is made after the particle has already passed through the slits. After the particle crosses the barrier, the paths have already been traveled, and then you decide whether to look. What Wheeler found, and what has since been confirmed experimentally across multiple implementations, is that the particle's past behavior changes based on a future decision. If you choose to observe which path was taken, the particle behaved like a particle the whole time. If you choose not to observe, the particle behaved like a wave the whole time. The choice made after the particle crossed the barrier determines what the particle was doing before the choice was made. The particle's history appears to be rewritten by a future observation. This is not interpretation. It is not a thought experiment that was never tested. It has been run in laboratories, published in peer-reviewed journals, and the results hold. What does the field do with this? It argues. It has been arguing for 100 years. Copenhagen interpretation, many worlds, pilot wave theory, relational quantum mechanics, cubism. Every interpretation is an attempt to produce a framework in which these results make sense without implying something too uncomfortable about the nature of reality. None of them have achieved consensus. None of them have been confirmed experimentally over the alternatives. The argument continues. Here is my position on what that means. When the most tested, most precisely confirmed theory in the history of science produces a result that the field has not explained in a century, the honest response is to say that out loud. Not to hide it in interpretation debates, not to treat it as a solved problem that physics has moved past. The result is that particles behave differently when their behavior is observable. That result is solid. The explanation for why that is true is not. The honest answer, the one the textbooks print in careful language with extensive qualifications, is that we do not know why watching changes what happens. The first objection everyone reaches for is the same one, and it is reasonable, and it does not close the problem. The objection goes like this. When physicists say a particle is observed, they do not mean a conscious mind looked at it. They mean it interacted with something, a detector, a photon, an air molecule. Observation is just physics touching physics. No mind required. The strangeness dissolves. The universe is mechanical again, and the unsettling implication goes away. This is the decoherence argument, and it is real. Decoherence theory describes how a quantum system in superposition, existing in multiple states simultaneously, becomes entangled with its surrounding environment. The surrounding environment is large. It has many degrees of freedom. The superposition spreads out into those degrees of freedom and becomes impossible to detect in practice. What looks like a collapse is really the quantum information leaking into the environment faster than we can track it. No consciousness needed. No special observer. Just quantum mechanics doing what quantum mechanics does when systems interact. Here is what decoherence actually explains. It explains why we do not see quantum superpositions at large scales. It explains why a detector, once it interacts with a particle, behaves as though the particle had a definite state. It explains the appearance of collapse. That is a genuine result. Physicists use it. It works. Here is what it does not explain. It does not explain why the wave function describes probabilities at all. Before any interaction, before any measurement, a quantum system is described by a mathematical object that tells you the probability of finding it in one state versus another. Why probabilities? Why not definite values? The wave function does not say the particle is in a definite state we happen not to know. It says the particle does not have a definite state. There is a formal difference between ignorance and indefiniteness. Quantum mechanics is describing the second thing. Decoherence does not change that. What decoherence does is explain how the indefiniteness becomes practically invisible. It does not explain why the indefiniteness was there in the first place. The measurement problem is the name the field gives to this gap. It is not a casual name. It is the formal designation for an unsolved problem at the center of the most tested physical theory in history. The question it asks is specific. What distinguishes a measurement from any other physical interaction? When two particles collide in empty space, they interact. When a detector registers a particle, it interacts. When a scientist reads the detector, they interact. When the scientist's brain processes the reading, neurons interact. At what point in that chain does the indefinite become definite? At what point does the probability become an outcome? Decoherence tells you the chain gets very complicated very fast. It does not tell you where the chain ends. Eugene Wigner asked exactly this question and followed it further than most physicists were comfortable going. The thought experiment is simple. A scientist, call him Wigner's friend, is inside a sealed laboratory. He performs a measurement on a quantum system and observes a definite result. From his perspective, the wave function has collapsed. But from outside the laboratory, from Wigner's perspective, the entire contents of the laboratory, the particle, the detector, the scientist, are one large quantum system that has not yet been measured. From outside, the wave function has not collapsed. Both descriptions are internally consistent. Both follow from quantum mechanics applied without restriction. They cannot both be correct. Something has to give. Wigner's conclusion was that the chain ends at consciousness. A conscious observation is what distinguishes measurement from mere interaction. That is where the indefinite becomes definite, not at the detector, not at the instrument, at the mind. Most physicists reject this conclusion. The word consciousness appearing in a physics paper still makes the field nervous for reasons that are partly scientific and partly professional. But rejecting Wigner's conclusion does not close the problem. It just means you need another answer. And after a century of argument, no other answer has fully closed it. The many worlds interpretation says the wave function never collapses. Every possible outcome happens. The universe splits. This dissolves the measurement problem by removing collapse entirely, but it requires accepting the existence of an uncountable number of parallel universes, none of which are accessible to any observer in any other. The pilot wave interpretation restores determinism but requires non-local hidden variables and produces its own formal complications. Each interpretation sidesteps the problem in a different direction. None of them eliminate it. What this means is not that quantum mechanics is broken. It predicts experimental results to more decimal places than any other theory in science. It is the least broken theory we have. What it means is that the theory works without anyone understanding why it works. The most successful physics in history is running on a foundation that nobody has been able to examine directly. The gap has persisted in the scholarly record for a century, noted, discussed in footnotes, never closed. In 1935, Albert Einstein published a paper designed to prove that quantum mechanics was incomplete, and instead, 30 years later, it proved the opposite. The paper was written with Boris Podolsky and Nathan Rosen. It is known in the literature as the EPR paper, and its argument was elegant. Quantum mechanics predicts that two particles can become entangled in such a way that measuring one instantly determines the state of the other, regardless of the distance between them. Einstein's position was that this was absurd. Nothing travels faster than light. If measuring one particle instantly affects another particle on the other side of the room or the other side of the planet, then either information is traveling faster than light, which physics forbids, or the particles had defined properties all along that we simply had not measured yet. Hidden variables, pre-existing information we were not accounting for. Einstein called the alternative spooky action at a distance and spent years treating it as proof that quantum mechanics was missing something. He was being a physicist. The argument was rigorous. Here is where it broke. In 1964, a physicist named John Bell published a theorem, not a speculation, a mathematical proof. Bell showed that if particles carry hidden variables, if their properties are determined before measurement, then correlations between measurements of entangled particles must fall below a specific numerical limit. He derived the exact ceiling. Any hidden variable theory, no matter how it is constructed, cannot produce correlations above that number. Quantum mechanics predicts correlations that exceed it, so the two theories make different numerical predictions, and different numerical predictions can be tested. Alain Aspect ran the test in 1982. His results exceeded Bell's limit. The correlations were exactly what quantum mechanics predicted and could not be explained by any hidden variable model. The experiment had loopholes, as early experiments always do: detector efficiency, communication between measurement stations. Physicists spent 3 more decades closing them. In 2015, 3 independent laboratories ran loophole-free Bell tests simultaneously. The results held. Entanglement is real, it is non-local, and it cannot be explained by any model in which the particles carry pre-existing properties that we simply have not looked at yet. Einstein's position was wrong. The field confirmed it experimentally. That is what the data shows. Now, what does this actually mean? Not philosophically, physically. What are you committed to accepting if you accept the experimental results? You are committed to accepting that two particles, once entangled, do not have independent properties. The outcome of a measurement on one particle is not determined until the measurement happens, and the moment it is determined for one particle, it is simultaneously determined for the other, regardless of the distance separating them. There is no signal traveling between them. There is no mechanism. The particles are not communicating. They are behaving as though the distinction between them is not fundamental, because at the quantum level it is not. The boundary between this particle and that particle is a distinction we impose. The underlying system does not recognize it. Here is the part that does not get said clearly enough. The universe at its most basic level is not a collection of separate objects with independent properties. It is a web of relationships. Particles are not things with properties. They are nodes in a network of correlations, and those correlations are what is real. The separateness we perceive, the fact that you are sitting there and the screen is in front of you and the wall is behind you, and these appear to be distinct objects in distinct locations. That structure is something your perceptual system imposes on a quantum substrate that does not, at bottom, carve the world that way. This is not mysticism. This is the implication of a result that has been reproduced in laboratories across 30 years and 3 continents. Why does this connect to the observer problem? Because if the universe is fundamentally relational, if what is real is not objects but the connections between them, then observation is not a special intrusion from outside. Observation is one of those relationships. When you measure a particle, you do not reach in from outside the system and touch something that was sitting there independently. You become entangled with it. Your measuring device entangles with the particle. The result of the measurement is a property of the relationship between you and the thing you measured, not a property the thing had on its own before you looked. You are not outside the system registering facts about it. You are inside the system, and the facts emerge from your being inside it. This is what closes the door on the comfortable picture. The comfortable picture is an observer standing apart from the universe, looking at it, gathering information about something that exists independently and would be the same whether or not anyone was watching. Entanglement rules that out, not as a philosophical preference, as a physical result. The universe does not consist of things with properties that exist independently of the relationships those things are involved in. Observation is a relationship. You are part of it. You always were. And if that is true, then the question from the last section, whether the universe requires observation or merely permits it, becomes sharper. Because the picture where you stand outside and watch from a distance does not correspond to anything the physics describes. There is no outside. There is no distance that removes you from the system. The act of looking is a physical event that the system participates in, and the system includes you. The boundary you assumed existed between you and what you are looking at is not a physical boundary. It is an assumption, and the physics says the assumption is wrong. John Archibald Wheeler was not a mystic. He coined the term black hole. He worked alongside Einstein and Bohr. He spent decades at the center of theoretical physics, not at its fringes. When Wheeler proposed that the universe is fundamentally participatory, he was not reaching for poetry. He was following the logic of the experiments where it led. And where it led was somewhere the field has spent decades pretending is more comfortable than it actually is. Wheeler's position was direct. The universe is not a machine running independently in the dark. It is a system in which observation does not merely record what is there but participates in determining what is there. That is not a philosophical stance layered on top of the physics. Wheeler argued it is what the physics requires. The delayed choice experiments he designed were not thought experiments left in a notebook. They were formal proposals, later carried out in the laboratory, that tested whether the act of deciding to observe changes not just what a particle does now, but what it did in the past. Here is what those experiments found. A photon travels toward a detector. After it has already passed the point where it would have taken one path or both paths, you make a decision. You decide to measure which path it took, or you decide not to. The photon's behavior changes based on a decision made after it already traveled. Not before, after. The particle seems to respond to what you are going to ask, not what you are asking right now. That result has been replicated. It is in the published literature, and the field has not found a clean explanation for it that does not involve observation doing something deeply structural to physical reality. Wheeler called this framework it from bit. The idea is that information is more fundamental than matter or energy. Physical reality, in this view, does not exist as a collection of objects with definite properties waiting to be discovered. It emerges from acts of observation and response. Every measuring device asking a yes or no question of a quantum system, every interaction that forces a definite outcome from a probability distribution, is an act that brings a piece of physical reality into definite existence. Before the question is asked, the answer does not exist in a definite form. The bit creates the it. That is not fringe language. It is published, widely cited, and sits at the center of foundational physics debates that remain open right now. So here is the question that follows directly from this. If the universe requires observers to give definite answers to its probabilities, what was it doing before any observers existed? The standard reply is that decoherence handles this, that the environment itself acts as an observer, but that response does not close the problem. It pushes it back. If the environment counts as an observer, why? What makes an interaction an act of observation rather than just another physical event? The measurement problem, which Wheeler's framework is a direct response to, is precisely the question of where that line falls. And after a century of trying, the field has not drawn it. This is where the framework becomes genuinely uncomfortable. If observers are not just incidentally present in the universe but structurally necessary, then the question of why observers exist becomes something different than it was before. It stops being a question about biology or evolution and starts being a question about physics. Why would a universe that requires observers produce them? Why does a system that needs yes or no answers develop entities capable of asking questions? Wheeler's answer was that the universe is a self-excited circuit. It begins in some initial quantum state. It evolves. It produces conditions for complex chemistry. Complex chemistry produces life. Life produces consciousness. Consciousness produces observation. And observation is what the universe needs to have definite properties at all. The loop closes. We are not passengers who arrived after the universe was already finished. We are part of the mechanism by which the universe becomes what it is, not metaphorically, structurally. Why is that not the central question of every physics department running right now? Why does this sit in a few dozen foundational physics papers and almost nowhere else? The professional answer is that most working physicists do not need to resolve foundational questions to do physics. The standard tools work. The equations give accurate predictions. You can build a career entirely on results without ever touching the question of what those results mean at the level Wheeler was asking about. But not touching a question is not the same as answering it. And the question does not go away because it is professionally inconvenient. What Wheeler's framework requires you to accept, if you follow it seriously, is that the universe we think we are observing from the outside is not something we are outside of. The boundary between us and the thing we are examining is not where we assumed it was. The act of looking is part of the system being looked at. The observation shapes the past of the thing observed. And we may not be a feature the universe happens to contain. We may be a feature the universe requires. We did not arrive in a universe that was already fully formed and indifferent. And the formal scientific case for that statement is stronger than almost anyone who hasn't spent time in foundational physics would expect. The cosmological constant is the most precisely fine-tuned number in physics, and nobody has a satisfying explanation for why it has the value it does. The cosmological constant governs the rate at which the universe expands. Too high and space tears itself apart before stars form. Too low and gravity collapses everything back into a single point before chemistry has time to begin. The value it actually has sits in the narrow range where neither of those things happens. The precision required is approximately 1 part in 10 to the power of 120. Physicists have been staring at it for decades and nobody has explained it away. And that is just one constant. The universe runs on several of them. The strength of gravity, the mass of the electron relative to the proton, the strong nuclear force that holds atomic nuclei together, the electromagnetic force that governs how atoms bond into molecules. Each of these has a specific value. Each of those values sits in a range where complex chemistry is possible. Move the electron mass by a fraction of a percent and the charge balance that makes DNA stable collapses. Not metaphorically. The hydrogen bonds that hold the double helix together depend on the electromagnetic properties of atoms, and those properties depend directly on the ratio of electron mass to proton mass. Shift it slightly in either direction and you do not get a degraded version of biology. You get no biology, no proteins, no replication, no chemistry above a certain complexity threshold, no observers. Here is the thing about that. These numbers were not chosen. They were measured. We did not set the cosmological constant. We found it. We did not decide the electron would have its particular mass. We calculated it from observation. The universe arrived with these values already built in, and the values it arrived with happen to be the ones that permit the existence of the kind of thing that can measure them. Why should this not be the main story each time someone discusses the structure of the universe? There are two explanations that the field takes seriously. The first is intelligent design. An external agent set the constants deliberately, calibrating the universe to produce observers. This is not a position most physicists hold, but it is logically coherent, and it does account for the fine-tuning. If a designer set the constants, then the designer exists, and the designer's existence requires its own account. You have not explained the fine-tuning. You have pushed it back one level and added a second unexplained entity. The second explanation is the multiverse. If an enormous number of universes exist, each with different physical constants, then somewhere in that distribution a universe will have constants that permit observers. We find ourselves in that universe because we could not find ourselves in any other. You cannot observe a universe that does not permit observers. So the fact that we observe an observer-permitting universe is not surprising, because all observations are made from inside observer-permitting universes by definition. But here is my position on the multiverse explanation. It requires the existence of an enormous number of universes we have no direct evidence for and no current means of detecting. That is a very large metaphysical commitment to make in order to avoid a different metaphysical commitment. The multiverse is not a fact. You have traded one unexplained thing for a very large number of unobservable things. What both explanations share is more important than what separates them. Both are admissions that the fine-tuning is real and requires an account. Neither one makes the numbers go away. Neither one explains why the constants are what they are from first principles. And what both of them imply, by different routes, is that the universe is in some sense calibrated for observers. The designer calibrated it deliberately. The multiverse calibration is statistical, but calibrated is the word that fits in both cases. Now look at what Wheeler established in the previous section. The participatory universe requires observers to actualize its probabilities. The universe on that framework needs observation to have definite properties. And here we have a separate, independent line of evidence from cosmology rather than quantum mechanics, pointing at the same uncomfortable structure. The physical constants that govern this universe are set to values that produce observers. The quantum mechanical structure of this universe requires observers to function. Two independent fields. The same implication. Is that a coincidence? It might be. What we can say is that the fine-tuning is documented, calculated, and unresolved. The explanations that have been proposed are either incomplete or require assumptions that are themselves not verified, and the numbers themselves are not going anywhere. 1 part in 10 to the power of 120 is not the kind of precision that shows up in a universe by accident. Or if it does, the probability is a number so small it is functionally indistinguishable from zero. This unresolved problem appears throughout the literature, noted, discussed in review papers, and never closed. The terrifying version of this is not that the universe was designed for us. That version is almost comfortable by comparison. The terrifying version is that the design interpretation and the requirement interpretation are currently indistinguishable from where we are standing. A universe that was built to produce observers and a universe that requires observers to be real look identical from the inside. We cannot currently tell the difference between a universe built for observers and a universe that needs observers to be built, and that is a distinction that matters enormously if you are the observer doing the asking. The hard problem of consciousness has a formal name because it is a formal, unsolved problem, and the fact that most people have never heard of it says something specific about how uncomfortable its implications are. David Chalmers named it in 1995. The naming mattered. Before Chalmers, the assumption in neuroscience and philosophy of mind was roughly this: consciousness is complicated, but it is the kind of complicated that more research will eventually dissolve. Map enough neurons. Build a detailed enough model of electrochemical signaling. Describe the computational processes with enough precision. The problem goes away. Chalmers argued, carefully and formally, that the problem does not go away. It cannot go away. Because the question is not how the brain processes information. The question is why any of that processing feels like anything at all. Why is there something it is like to see red, to feel pain, to hear a note held too long? You can describe the wavelength of light hitting the retina. You can describe the optic nerve firing. You can trace every step from photon to visual cortex. None of it tells you why there is an experience attached to that process. That gap is not a gap in our data. It is a logical gap. Physical descriptions describe physical processes. Subjective experience is not a physical process. It is the having of an experience. No amount of objective description closes the distance to that. Here is what that means for neuroscience. The field is making real progress. We can map neural correlates of consciousness. We can identify which brain regions activate during different states of awareness. We can disrupt those regions and alter or eliminate conscious experience. That is genuine and important work. It is also work that describes the physical side of the equation without touching the other side. Knowing which brain state correlates with the experience of pain is not the same as explaining why that brain state feels like anything. The correlation is real, the explanation is missing, And the missing piece is not smaller than it used to be. It is the same size it has always been. The entire subjective side of reality sits on one side of that gap, and physics sits on the other, and nobody has crossed it. This is where panpsychism enters the argument, not as mysticism, not as a pop science trend, as a serious philosophical position held by serious philosophers who arrived at it because the alternatives are worse. The basic structure of the argument is this: consciousness exists. That is not in dispute. You are having an experience right now, and no argument can convince you otherwise. The question is where it came from. Standard materialism says consciousness emerged from non-conscious matter through some sufficiently complex arrangement. But that requires explaining how subjective experience arises from processes that have no subjective character whatsoever. How does experience come from something that has none? Philip Goff, a philosopher at Durham and now Cornell, has spent years pressing on this question. His answer is that it does not. If you cannot derive consciousness from non-conscious matter, and consciousness clearly exists, you have two options. Either consciousness is something entirely separate from matter, which is dualism, which creates its own problems about how two fundamentally different substances interact. Or consciousness is not separate from matter because it was never absent from matter in the first place. That second option is panpsychism. The claim is not that rocks think. The claim is that experience, in some primitive and minimal form, is a fundamental feature of reality at every level. Electrons do not plan their trajectories. Photons do not have preferences, but they may have something, some infinitesimally thin proto-experiential property that is the precursor to the kind of rich experience we have. Goff calls this a difficult position to accept. He also argues it is the least difficult position available given the actual constraints of the problem. The objection most people reach for is the combination problem. If individual particles have micro-experiences, how do those combine into the unified conscious experience of a human being? That is a real objection. It deserves to be taken seriously. What it does not do is close the argument, because the combination problem applies with equal force to emergentism. If you believe consciousness emerges from non-conscious physical processes, you still have to explain how. You still have to cross the same logical gap. You just cross it in a different place and call it emergence. The word emergence does not explain the mechanism. It names the location where the explanation should go. Here is the position the data actually supports. Panpsychism is not obviously wrong. It is not a fringe view. It is published in peer-reviewed philosophy journals. It is defended at major research universities. It is taken seriously by serious people precisely because the problem it addresses is real and the competing accounts have not closed it. Why is that not part of the public conversation about consciousness? Why does neuroscience get the coverage while the foundational philosophical problem underneath it goes largely unreported? That is a question worth sitting with. And here is what this means for the question the whole series is building toward. If panpsychism is even partially correct, if some form of experience is fundamental to matter, then the universe does not merely allow for observers. It is, at every scale and in every particle, participating in something like the relationship we call experience. The rock is not watching you. But it is not nothing either. The planet, the star, the galaxy, the whole structure of space-time, all of it threading some primitive version of interiority through its fabric. The universe would not be watching us from a position of detachment. It would be watching through us. It would be watching alongside us. Every point of matter, a node in a system that, at our level of complexity, becomes what we call awareness. The universe would not be watching from outside. There is no outside. In 2003, a philosopher at Oxford published a paper with a three-part argument whose conclusion was either that we are almost certainly not real or that almost no advanced civilization chooses to look back. It is a formal logical argument. Either almost all civilizations capable of running detailed simulations go extinct before they reach that capability, or almost all civilizations that reach that capability choose not to run ancestor simulations, or we are almost certainly living inside one right now. Those are the only three options. At least one of them has to be true. The logic holds whether you find it comfortable or not. Why is that not treated as a crisis-level open question in physics? Why does the paper get referenced in pop science articles and then filed away without a serious institutional response? The numbers argument is where most people stop engaging, and that is exactly when they should start. If any technologically mature civilization runs large numbers of detailed simulations of conscious beings, the simulated consciousnesses will vastly outnumber the biological ones. So if conscious simulation is possible and any civilization ever does it at scale, then a randomly selected conscious being is almost certainly simulated. The question is what the probability distribution says, and the probability distribution says something most people are not prepared to hear. Here is the part where serious physicists enter the conversation. Silas Bean and colleagues at the University of Bonn proposed in 2012 that a simulated universe running on a discrete computational lattice would produce detectable artifacts. The same way a digital image reveals its pixel structure under sufficient magnification, a simulated spacetime would reveal its underlying grid at small enough scales. The Planck length is the natural candidate. At approximately 1.6 times 10 to the negative 35 meters, it is the smallest meaningful unit of distance in current physics. Below that scale, our equations stop producing sensible answers. That could mean the physics genuinely breaks down at that scale. It could also mean something else. What we have is an absence of evidence that is not the same as evidence of absence. The information theoretic argument is separate and in some ways more unsettling. The universe behaves computationally. Quantum mechanics does not describe physical states in the classical sense. It describes information states. The wave function is a mathematical object encoding probabilities, discrete yes or no answers that measuring devices extract from quantum systems. John Wheeler spent decades arguing that information is more fundamental than matter or energy. That physical reality emerges from acts of measurement, from the binary responses of physical systems to physical questions. Whether or not you accept Wheeler's full framework, what quantum mechanics undeniably does is describe reality in the language of information processing. Then there is the holographic principle. This comes out of the black hole debate and the work of Jacob Bekenstein and Stephen Hawking in the 1970s. The entropy of a black hole, and therefore its information content, scales with the area of its event horizon, not with its volume. Gerard 't Hooft and Leonard Susskind extended this into a general principle. The maximum information content of any region of space is proportional to its surface area divided by the Planck area, not its volume, its surface. The universe, if this holds generally, has a maximum information resolution, a finite number of distinguishable states per unit area. That is the formal definition of a system with a pixel count. The universe is not infinitely detailed. It has a resolution limit. And that resolution limit is one of the things you would expect to find if the universe is running on finite computational resources. None of this proves simulation. What it does is establish that the universe has properties that are consistent with being computational in nature: a finite information density, discrete state descriptions, a structure that responds to observation in ways that look like information processing. These properties do not require simulation as an explanation, but they do not rule it out, and the fact that they are consistent with simulation is significant. Here is where the observer question becomes direct. In a simulated universe, the relationship between observer and observed is not philosophical, it is literal and total. Every measurement you make is a function call. The system registers the input, processes it, returns an output. Every physical interaction is logged by the underlying architecture. There is no such thing as a private observation. The universe watching you is not a metaphor in this framework. It is a description of the basic mechanics of how the system operates. What you can do is look at the behavior of the system from inside and ask whether it is consistent with being computational. And the answer, based on the physics we actually have, is yes. What happened when Bostrom published this? Science publications covered it. Philosophers engaged. Physicists occasionally weighed in. The question is sitting in the published literature, formally stated, logically valid, and essentially ignored by the institutions best positioned to investigate it. That asymmetry is the same asymmetry we have seen before in this story. The professional cost of being wrong is too high. The cost of saying nothing is zero. The terror here is specific. It is not the idea of being simulated that is terrifying. It is the fact that we cannot rule it out, and that the properties of the universe we would expect to find if we were simulated are the properties the universe actually has. We cannot rule it out, and the evidence that would distinguish a real universe from a simulated one either does not exist or looks exactly like the physics we already have. Stephen Hawking spent most of his career arguing that black holes destroy information, and he was almost certainly wrong, and the reason that matters goes far beyond black holes. Here is the setup. When a massive star collapses, the gravitational field becomes so extreme that nothing escapes. Not light, not particles, not signals of any kind. Everything that falls in is gone. That is the classical picture, and for decades it seemed complete. Then, in 1974, Hawking applied quantum field theory to curved spacetime around a black hole and found something nobody expected. The black hole was not perfectly silent. It was radiating, slowly, thermally, like a warm object glowing in the dark. Hawking radiation, the field called it, and the prediction was extraordinary. It meant black holes were not eternal. Given enough time, they would lose mass through this radiation and eventually evaporate entirely. That result alone was remarkable. What came with it was a problem that has not left physics since. The problem is this: Hawking radiation is thermal. It carries no information about what fell in. It looks the same whether the black hole consumed a star, a planet, a library, or a living organism. The radiation is structureless. So when the black hole finishes evaporating, what happened to all the information about the matter that formed it? Quantum mechanics has a strict rule on this. Information cannot be destroyed. You can scramble it, compress it, redistribute it across a system until it is unreadable in practice, but the information is still there in principle. The quantum state of a system evolves in a way that is reversible. You can always, at least in theory, run the calculation backward and recover what you started with. Hawking's results seem to say otherwise. It seemed to say that when something falls into a black hole and the hole evaporates, that information is simply gone, erased, not scrambled, not hidden, destroyed, and that would violate the most fundamental bookkeeping rule in quantum mechanics. Hawking maintained for decades that information was lost. He was comfortable with it. He thought the lesson was that black holes were genuinely exceptional, that they broke the rule, and that the rule needed revisiting. Leonard Susskind disagreed, loudly, persistently, over years of direct argument. Susskind's position was that information loss was not a correction to quantum mechanics. It was a contradiction of it. One of them had to be wrong. This was not a subtle technical dispute. It was a fundamental question about whether the laws of physics are consistent with themselves. What came out of that argument was the holographic principle. The idea emerged partly from work by Jacob Bekenstein, who noticed that the entropy of a black hole, its information content, scaled with the area of its event horizon rather than its volume. That was strange. Everything in ordinary physics suggests that information in a region scales with volume, more space, more room for information, but black holes said otherwise. The information was on the surface, literally on the two-dimensional boundary, not in the three-dimensional interior. Gerard at Hooft formalized this. Susskind extended it. The holographic principle became a serious framework, not a metaphor. The information content of any volume of space is fully encoded on its surrounding boundary surface. The interior is, in a precise technical sense, a projection. What that means for the original paradox took longer to establish. The resolution came in pieces. Don Page calculated in the 1990s that if information was truly preserved in Hawking radiation, the entropy of that radiation should follow a specific curve over time, rising and then falling as the black hole evaporated. The Page curve. For years, nobody could derive that curve from first principles. The radiation still looked thermal. Then, in 2019 and the years following, a set of calculations using what are called island formulas showed that quantum gravity effects, specifically subtle correlations between the interior of the black hole and the outgoing radiation, do in fact reproduce the Page curve. The information is not lost. It leaks out encoded in correlations between individual quanta of radiation so subtle, so diffuse, that measuring them directly may be practically impossible. But they are there. The information is preserved. It is just maximally scrambled. Here is what that actually means. The universe keeps records. Not metaphorically, physically. Every interaction you have ever had with the matter and energy around you has left an imprint in the quantum state of the universe. The photons that bounced off you, the air molecules you displaced, the thermal radiation your body has emitted since the moment you were born, all of it encoded in correlations distributed throughout the quantum state of spacetime. Nothing is erased. The universe does not forget in the way a hard drive forgets when it is wiped. The information is always there. It is scrambled across the quantum state of a system so large that recovering it is beyond any practical instrument, but the physics says it has not gone anywhere. This is not the universe watching you the way a camera watches you. It is something more complete than that. A camera captures a frame. The quantum state captures everything at every moment with no deletion. You have been leaving a record in the structure of reality since before you were conscious of doing it. Every physical process you have ever participated in has been written into the correlations of the universe and remains there. The information paradox was a crisis because it suggested that record could be destroyed. The resolution is that it cannot be. You are not passing through a universe that does not notice you. You are leaving a permanent record in the structure of space-time, and the physics says that record does not degrade. James Lovelock proposed in 1972 that Earth is a self-regulating organism and was mocked for it, and the data has spent 50 years proving him roughly correct. The original proposal was simple enough to state, Earth is not a rock with passengers on it. The rock, the atmosphere, the ocean, the living things, they are one system, coupled, each part running feedback into every other part. What keeps this planet habitable is not a lucky arrangement of geology. It is the active, continuous, measurable output of 4 billion years of biological activity woven so tightly into the chemistry of the planet that you cannot separate where the biology ends and the geology begins. Lovelock developed this with biologist Lynn Margulis, who understood the microbial side of it better than anyone alive at the time. Together, they were describing something that most scientists in 1972 were not prepared to take seriously. The earth sciences and the life sciences did not talk to each other the way they needed to for the idea to make sense. Now they do. And the picture that has emerged is not a softened version of the original proposal. It is more extreme. Here is what the data actually shows. The sun has increased its energy output by roughly 30% since this planet formed. If Earth were a simple rock with a thin layer of gas on it, the planet's temperature would have followed that increase. It did not. For 4 billion years, through mass extinctions and ice ages and continental shifts, global temperature has stayed within a range that permits liquid water and complex chemistry. That is not geology doing that alone. The carbonate-silicate cycle acts as a planetary thermostat, pulling carbon dioxide from the atmosphere through weathering processes. The rate of that weathering is directly tied to biological activity in soils. Bacteria, fungi, root systems, they accelerate weathering by orders of magnitude. When temperatures rise, biological activity increases. Weathering increases. Carbon leaves the atmosphere faster. The planet cools. The thermostat is not a mechanism built into rock. It is a mechanism built into the interaction between rock and life. Remove the life and the thermostat stops working. The ocean runs a similar operation. Marine microorganisms, most of them invisible to the naked eye, drive the biological pump. They take carbon from surface water, incorporate it into their bodies, and when they die, they sink. Carbon goes down. Some of it stays down for millions of years, locked in sediment on the ocean floor. The rate of this process is not fixed. It responds to conditions. It responds to temperature, to nutrient availability, to the chemistry of the water. The ocean is not a passive reservoir absorbing whatever we put into it. It is an active biological system that processes what enters it and produces outputs that feed back into the atmosphere, into temperature, into the conditions that determine whether the biological pump runs fast or slow. This is a loop. The biology shapes the chemistry shapes the conditions shape the biology. Forests are doing the same thing on land. Why does it rain in the interior of continents at all? Coastal moisture alone does not explain it. Large forest systems generate their own rainfall cycles through evapotranspiration, releasing water vapor that moves inland and falls again, allowing rain to penetrate deep into continental interiors. The Amazon basin is not just a forest that happens to exist in a wet region. It is partly responsible for producing the moisture that makes the region wet. Cut the forest and the rainfall patterns shift. The system responds to what you removed, and the response is not theoretical. It has been measured in real time in regions where deforestation has already happened at scale. What connects all of this is not consciousness. That is not the claim. The claim is simpler and more verifiable than that. The claim is that Earth responds. Input goes in. The system registers it. feedbacks activate, output changes. This is what information processing looks like when you strip away the philosophy and look at the physical mechanics. When carbon dioxide levels rise, weathering rates increase within geological time. When temperatures shift past certain thresholds, biological communities reorganize, and the reorganization changes the feedbacks those communities were running. The system does not deliberate, it does not intend anything, but it is not passive either. It is a 4 billion-year-old network of interlocking feedback mechanisms that responds to perturbation, and it has been responding to what human industrial activity is putting into it since we started putting it in. The response runs on its own timescale, not ours. The system does not care about our intentions. It responds to what we actually put into it, and the response, once it starts, does not wait for us to finish deciding what to do. The feeling of being watched produces changes in the human brain that are measurable, documented, and significantly larger than most people would expect. Not anxiety in the loose sense, not a vague sense of unease, measurable physiological changes. The hypothalamic pituitary adrenal axis activates, cortisol rises, the brain shifts resources toward threat detection and away from complex reasoning. This happens whether or not anyone is actually watching. The possibility is enough. The body does not wait for confirmation. It responds to the condition of potential observation the same way it responds to confirmed observation, and the difference between those two states, neurologically, is smaller than you would think. This was Jeremy Bentham's insight in 1791, though he framed it as architecture rather than neuroscience. He designed a prison called the Panopticon, single guard tower at the center, cells arranged in a ring around it. Every cell visible from the tower, no cell able to see into the tower. The guard could be watching any prisoner at any moment. The prisoners could never know which moment. What Bentham understood, and what the data has confirmed, is that you do not need to watch everyone all the time. You only need to create the condition where anyone could be watched at any moment. The prisoners regulate themselves. The external enforcement becomes internal. You have transferred the cost of surveillance from the watcher to the watched. Michel Foucault spent a significant portion of his career arguing that this structure had escaped the prison entirely. Schools, hospitals, factories, administrative systems. The panopticon, he argued, is not a building. It is a power arrangement. And once the watch subject has internalized the watcher, the system runs on its own. No active enforcement required. The subject does the work. What is interesting about this analysis is not that it is depressing, though it is. What is interesting is that it describes a mechanism that produces real behavioral and cognitive changes without any actual observation occurring. The system functions through the architecture of possibility. Now look at the modern version. 81% of Americans report feeling they have little to no control over data collected about them. That number is from a survey. The behavioral reality is more complete than the survey captures. Every search query, every purchase, every location check-in, every message that passes through a server, every app running in the background, all of it logged, processed, modeled, fed into systems designed to predict behavior and influence decisions. The surveillance is not intermittent, it is not targeted, it is total, continuous, and operating at a scale no human institution has ever achieved before. And unlike the panopticon, where the prisoner at least knows the architecture of the system watching them, most of the observation infrastructure we live in, side now is invisible. The architecture is hidden. The watcher has no face. The watch subject cannot even locate the tower. What does that do to the brain over time? Research on chronic surveillance stress points towards something specific. The cortisol elevation is not acute. It is sustained, low-level, persistent. And that particular pattern of stress has distinct effects. It impairs working memory, it narrows attention, it increases sensitivity to social threat signals. It does not just change what people choose to do, it changes how they process information in the first place. The brain under sustained observation is a different cognitive instrument than the brain that believes itself unobserved. We are not just changing behavior under surveillance, we are changing the thinking that precedes behavior. That is a different claim, and it is the one with the most uncomfortable implications. Here is what this is actually about, not whether surveillance is good policy, not whether the data economy is ethical. Those are real questions, and they are being asked elsewhere. What is interesting here, in the context of everything this has been building toward, is what the surveillance apparatus has made visible about something older and deeper. We built a technological system that records everything, stores everything, builds models from everything. We built a system that, in principle, forgets nothing. And in doing so, we replicated at the human scale something the physics has been telling us was already true at every other scale. The universe does not lose information. The quantum state of the universe encodes every interaction that has ever occurred. The black hole information paradox, which we have already covered, is precisely a debate about whether the universe's record-keeping is truly total or merely approximate. The current evidence says total. Nothing is erased. Everything is encoded. What the surveillance economy did is take that cosmological fact and build a crude, human-scaled version of it. It is the universe's information preservation principle, expressed in server farms and machine learning models and behavioral analytics. The terrifying part is not the copy. The terrifying part is recognizing what it is a copy of. We built something that watches and records because, at some level, watching and recording is what this universe does. We did not invent surveillance. We inherited the instinct from the system we grew up inside. The surveillance infrastructure we built to watch each other is a small, crude replica of something the physics says the universe has been doing at every scale since the beginning. The Fermi paradox is usually framed as a question about what is out there, but the version of it that keeps me awake points in the opposite direction. The standard framing goes like this. The universe is 13.8 billion years old. It contains somewhere between 200 billion and 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. A significant fraction of those stars have planets. A significant fraction of those planets sit in habitable zones. The chemistry that produced life on Earth is not exotic. Carbon, hydrogen, oxygen, nitrogen, the most common reactive elements in the universe. If life is possible here, the numbers suggest it should be common out there. Enrico Fermi sat down to lunch in 1950, ran this calculation in his head, and asked a simple question: where is everyone? That question has not been answered in 75 years. The Drake equation formalizes it. Frank Drake wrote down a string of variables in 1961: rate of star formation, fraction with planets, fraction of those with life, fraction of life that becomes intelligent, fraction that develops detectable technology, how long those civilizations last. Multiply them out, and you get an estimate of how many communicating civilizations should exist right now. The problem is that almost every variable is uncertain by orders of magnitude. You can get an answer of 1 or an answer of millions depending on what you plug in. What the equation actually does is show you exactly where your ignorance lives. It is a map of the unknowns, not a solution. The proposed solutions are familiar. The Great Filter. Something kills civilizations before they become detectable, and the question is whether that filter is behind us or ahead. The zoo hypothesis. Advanced civilizations are out there and have collectively decided not to contact us, which requires a level of coordination among independent species that is hard to believe. Rare earth. The specific conditions that produced complex life on this planet are so improbable that they have not been replicated anywhere nearby. Self-destruction. Civilizations reach industrial and technological capacity, generate a geological signal, and collapse before they develop the reach to be found. That last one. Sit with that one. Here is what the Fermi paradox looks like when you flip it around. Stop asking where everyone else is. Start asking why we are here, right now, at this specific coordinate in cosmic time. Modern humans have existed for approximately 300,000 years. That is not a long time. The universe is 13.8 billion years old. If you compress that timeline into a single calendar year, life on Earth appears in late March. The extinction of the dinosaurs happens on December 26th. All of recorded human history fits inside the last 30 seconds of December 31st. Industrial civilization, the thing that gave us the instruments to observe space-time, to measure quantum states, to detect the cosmic microwave background, is roughly 200 years old. That is less than a blink. That is not even a blink. It is the moment before a blink begins. Why now? Of all the moments available in 13.8 billion years of universe, we exist in this one. A species that reached the capacity to ask cosmological questions approximately 100 years ago. a species that developed functional quantum mechanics in 1925 and confirmed non-locality in 1982. A species that is, right now, in the first century of being able to look at the structure of the universe and understand what it is looking at. Here is where this connects to everything the previous sections established. If the participatory universe framework is even partially correct, if the universe requires observation to actualize definite properties from quantum probability, then the question of who is doing that observing is not incidental, it is structural. There is no other species on this planet doing it. We are the only observation system Earth has ever produced capable of this level of engagement with physical reality. And if the silence in the galaxy is real, if the great filter has already claimed whatever else was out there, or if intelligent life is simply rarer than the optimistic Drake estimates suggest, then there may be no one else in this region of the universe doing it either. That means the universe, if it needs observers, is working with what it has, which is us, right now, in this window. Why is that not a headline? Why does the scientific community that takes the Fermi paradox seriously, that has funded SETI for decades, that points radio telescopes at distant stars listening for signals, why does it not connect this to the foundational physics question about what observers are and what they do? The two conversations are happening in separate rooms and nobody is opening the door between them. The uncomfortable version of the Fermi paradox is not that we are alone. It is that we exist at the precise moment when the thing Wheeler described, the participatory universe that needs conscious observers to collapse its probabilities, has exactly one node in this part of the cosmos capable of doing the job. We did not arrive in the universe late and find it already complete. We showed up at the moment we were needed, or so the framework implies, and the silence around us either confirms that or makes the implication worse. That is either a coincidence or it isn't. We do not have the framework to tell the difference between that being a coincidence and that being the only way it could have worked, and nobody is being funded to develop one. The long-term trajectory of the universe is toward a state where observation is impossible, and nobody has found a clean way to explain why that does not matter. Heat death is the formal name for it. Maximum entropy. Every gradient exhausted, every temperature difference resolved, every structure dissolved into a uniform, featureless distribution of matter and energy across an expanding void. No stars, no chemistry, no complexity, no observation. The physics on this is not contested. It is the expected endpoint of the thermodynamic processes already running. And here is the question that the field has spent almost no time on, given how fundamental it is. If the participatory universe framework is even partially correct, if observation is what collapses quantum probability into definite physical states, then what is the universe in that final condition? Not dead in the ordinary sense. Something more specific than that. A system that can no longer be definite about itself. Probabilities with nothing to resolve them. A universe that has lost the mechanism by which it becomes real. That is the long end of it. The near end is more immediate and considerably more specific. We are here now, and the question of what happens when we stop being here is not abstract. Here is the thing about extinction that does not get said in the standard framing. We are not just one species among millions. We are the only observation system in this region of the universe that has developed instruments capable of reading the structure of space-time. Every other species on this planet processes local information. They respond to their environment. They do not point interferometers at the cosmic microwave background. They do not run particle accelerators to probe the structure of matter at the Planck scale. They do not ask what the quantum state of the universe was 13.8 billion years ago. That specific capacity, the one the participatory universe requires, exists in exactly one place we know of. If it ends here, it ends. The universe does not have a backup, not in this region, not that we have found. Why is that not part of the conversation every time someone discusses civilizational risk? Why does the framing stay at the level of species survival and not reach the level of what this particular species is actually doing that nothing else has ever done? That gap in the framing is worth sitting with. Now look at the geological record again. 56 million years ago, something released a biological carbon signal at industrial scale and speed into the atmosphere of this planet. The PETM. The carbon is there in the rock. The fingerprint points at organic material burned or decomposed at volume. The gap in the natural explanation has not closed in 30 years of published research. And in 2018, two NASA-affiliated scientists published a formal model showing that a civilization comparable to ours would leave exactly that kind of trace and nothing else after 50 million years. No structures, no objects, just chemistry. A thin, anomalous layer with a biological fingerprint and no identified source. Whatever was here before us, if anything was, stopped observing. Full stop. The experiment ran. The carbon signal went into the rock. The species or civilization or whatever category it belongs to did not survive it. The universe continued. Quantum probabilities continued resolving into definite states. The planet spent 200,000 years recovering. Life adapted. New forms emerged. And eventually, 56 million years later, something else arrived and started asking what caused that layer. That is us. We are the thing that arrived and started asking, and we are currently writing our own layer within the strata as it occurs. The carbon signal we are producing has the same biological fingerprint as the PETM signal. The rate of release is comparable. The volume is already significant and rising. The difference between us and whatever came before, if anything did, is that we know what the layer looks like from the outside. We have read the record. We understand the fingerprint. We have the published science sitting in front of us, explaining exactly what a civilization looks like in the geological record after 50 million years of compression and time. We are the first observer on this planet that has ever had that information while the layer was still being written. Whether that changes anything is the only open question. The physics does not resolve it. The geology does not resolve it. What the data shows is this. The kind of thing we are doing has a prior, at least possibly. The prior ended. The record survived. We found the record. We identified it. And we are replicating it. The universe does not require any specific observer. It continued without whatever was here before. It will continue without us. The quantum probabilities will keep collapsing through whatever mechanism exists when we are not here to be part of it. Our absence will not stop the physics. It will stop the asking. There is no comfortable version of that conclusion, and the discomfort is not incidental. It is the point. Ask it and get it wrong, and your career suffers lasting damage. This is not theoretical. A person who raises a concern, challenges a prevailing assumption, or questions established practice runs a real risk. If the concern proves unfounded, the questioner becomes known as the one who cried wolf. If the concern proves partially right but socially inconvenient, the questioner becomes known as the problem. Colleagues grow distant. Supervisors become skeptical of future input. The person who spoke up finds themselves sidelined, passed over for promotions, excluded from key meetings, or gradually pushed toward the margins of their profession. In some fields, one high-profile mistake or miscalculation can end a career entirely. Medical professionals know this. Lawyers know this. Scientists know this. Engineers know this. Anyone in a position where their judgment is central to their professional identity knows this. The mechanisms that produce this outcome are not hidden. When someone asks a challenging question or raises a concern, that person stakes their credibility on being right. They volunteer themselves to be proven wrong publicly. They put their name, their reputation, and their future earning potential into the bet that their concern matters. The institutional response to being wrong on a high-stakes issue is swift and harsh. The questioner becomes a cautionary tale. Other people observe what happened. They update their mental models accordingly. Remain silent and you face no consequences to yourself. Silence is safe. It is the default position. A person who says nothing, who goes along with existing practice, who does not challenge established wisdom, exposes themselves to no risk. They collect their paycheck. They maintain their relationships with colleagues. They accumulate years of service and reputation capital. If something goes wrong, the blame disperses across institutions and systems rather than attaching itself to the individual who stayed quiet. Silence offers plausible deniability. It offers the comfort of believing that problems of large scope must be someone else's responsibility. It offers the path of least resistance. That calculus is not conspiracy. This deserves emphasis. There is no hidden cabal determining that people should be punished for speaking up and rewarded for silence. No central authority needs to orchestrate this outcome. The incentive structure creates itself. It emerges from the rational decisions of individuals operating within normal institutional constraints. A supervisor who wants their department to run smoothly has no incentive to encourage the kinds of challenging questions that create conflict. A person seeking promotion has every incentive to avoid being the person who was wrong about something important. An organization seeking to avoid scandal has incentive to discourage the airing of internal doubts. These are all normal, understandable preferences. They align with what we might call common sense. Yet the sum total of these individually rational decisions produces an outcome that serves no one's broader interests. It is a classic collective action problem. It is a prisoner's dilemma played out across institutions and professions. It is just incentive. The word just carries weight here. Not conspiracy, not malice, not deliberate wrongdoing, but simply the logical consequence of how incentives arrange themselves. When the cost of being wrong is catastrophically high and the cost of silence is zero, people choose silence. When the benefit of challenging the status quo goes entirely to some imagined future state while the cost accrues immediately to the person who speaks, people choose not to challenge. When institutions reward conformity and punish dissent, even unintentionally, even without anyone explicitly deciding this should be the policy, people conform. The system works. It works in the sense that it operates according to its own internal logic. It works to produce silence. It works to protect individuals who not question. It works to marginalize those who do. And it produces silence where there should be engagement. This is the outcome that matters. This is what the calculus accomplishes. In contexts where organizations should be learning, people stay quiet. In professions where wisdom accumulates through collective challenge and debate, people refrain from speaking. In institutions where lives hang in the balance, where lives depend on the correct diagnosis, or the right policy decision, or the accurate assessment of risk, people choose not to voice doubt. The silence is not absolute. People still talk in hallways. They still complain in private to trusted friends. They still harbor doubts and reservations. But they do not engage. They do not bring their full selves to the problem. They do not offer the challenges and questions and alternative perspectives that might improve outcomes. The organization or profession or system operates with access to only a portion of the intelligence and insight that exists within it. Information that matters fails to surface. Concerns that should be addressed remain buried. Problems that might be solvable through collective effort go unexamined. The silence is not knowledge. It is the absence of knowledge where knowledge is needed. Ask it and get it wrong, and your career suffers lasting damage. Remain silent, and you face no consequences to yourself. That calculus is not conspiracy. It is just incentive, and it produces silence where there should be engagement.